Good morning, everyone. So today I'm Tiana or Ardila, that I would like to teach about the biochemical and engineering thermodynamics, which is this subject. It's very important in the chemical engineering, especially if you go to the works later or as the process engineer, we would like to design some equipment in the process. So we really need the thermodynamics because you will calculate how much the energy that you need and then the cost and how efficient your process. So thermodynamics, from the word we can define like thermo is actually it's heat and dynamics it means moving. So if you would like to discuss about the thermodynamics, it's regarding about the moving heat. So normally we just discuss about like how efficient all of the energy based on the heat transfer, or you can say that the thermodynamics. So in this case, we have the basic law and the concept of thermodynamics. I believe that all of you already learned in the senior high schools about the thermodynamic laws. We have 1 to 3 for the thermodynamics laws, but mostly we will use the first and the second law thermodynamics. So the application for the first and the second law of the thermodynamics we can apply in the steam gauge. Steam gauge is for the uh, if you go to the power plant, maybe you will see like the steam power plant to produce how they produce the electricity, and we can use the steam gauge to measure the pressures and the physical properties chart. This is mostly that we will apply in the course is how to read the charts. So all of the entropy and enthalpy we could define from the physical properties chart. So in the chapter 3, we will discuss more about the energy, how to read the enthalpy and entropy based on the charts. So also we have the Euler diagram. So Euler diagram is mostly used if you supposed to be would like to calculate like the efficiency or the quality of your steam. So based on the one charts, you may have 3 or even like 4 or 5 data in the same time. So you can determine the quality of your steam, the temperature, the pressure, the enthalpy, and then this is good or not for your boiler, for example. So because in the sum of the equipment, we cannot use all of it totally like the with the quality of the low quality of the steam. For example, like if you would like to use the turbine as the engine, so the turbine you need to have the qualities at least like larger than 90%, because if you have the water contained in the steam, it will affect the quality of the turbine itself. So they will easy to corrosion, they will easy to broken because you have the liquid contains inside our steam. And the other, it was the thermal power conversion cycle, like how much the conversions of your thermal that can be generated for the power. So this is mostly we will use the TS diagram. It's the temperature and then the entropy diagram. So you will see later like how the entropy will affect with the temperature. Please remember about the second law of thermodynamics. So when you discuss about the law of thermodynamics, you cannot just discuss about the first law and how to calculate only the enthalpy, because we always have also this, we need the second law of the thermodynamics, or you need to calculate the entropy to calculate the efficiency of your engine. So later I will discuss further about these laws. No wonder. So we have the calculation of the thermal properties of the pure fluids. So the thermal properties of the pure fluid, it's very important in thermodynamics because each of fluids. So when you say that each of the fluids, they consist of the three phase, solid, the gas, and then the liquid phase. So when you discuss about these three different kinds of phase, they will affect the thermal property relationship. For example, density. So density, if you increase the density, you would like to obtain the higher density, so you need to operate at low temperature. So the density is the function of the temperature, similar like the viscosity. So when you calculate, for example, I can give the example here. If you would like to design some equipment, in this case, we just use the pipe. Let's say if you have the pipe, so the pipe, you will have the fluid flow go in and go out. So if you would like to manage the fluid flow inside, which is the laminar or turbulent based on their flow rate, if you would like to define laminar flow, so you should operate or you should control the property of your fluid, so the velocity it will be constant. They will remain as a constant property. So in this case, like we should have the thermal properties of the fluid. In the other case, if you discuss about the binary mixtures, when I discuss about binary mixtures, it consists of the two systems at least. So let's say here I give you the example CO2 with the amine. Yeah. This is for the application CO2 absorptions. So CO2 and amine, they have somehow, if you check the curve, we have the bubble point, we have dew point. This is the binary curve is like 180 degrees cycles if you cut. Yeah, so in this case, that the highest point, this is we define as the critical points, which is the phase between the vapor and then the liquid phase. You cannot distinguish each other. So in this case, if you would like to separate, for example, I would like to separate two mixtures, but I operate at the critical points. So I couldn't separate these two liquid phase or these two phases. So in this case, we need to know the thermal properties based on each characteristic of the pure fluids. And the other is state equations. So what's the important equation here? It's not all of in the thermodynamics we can calculate by based on the, we can say that or based on the calculations. Yeah, of course we need the experimental data. So mostly in the experimental data you will get the pressure, temperature, and the volume. So this is PVT, is we call it, this is measurable variables. So you have P, pressure, volume, and the temperature. So when you would like to calculate the pressure, specific pressures, of course you need to have the experimental data. So suppose if you have limit experimental data, so your experimental data is not much, so you need to use some equation to predict your properties. So in this case, if you operate, for example, like low to the moderate, we can use the activity coefficients models like the non-random to liquids NRTL. We have also Wilson, we have Margules. So this all you can use low to moderate pressures. But how about if you have the high pressures? So the high pressure itself, we can use the equations of state. So later we discuss in the chapter 6 about the state equations, and the other is corresponding state. So corresponding state, it's regarding about the residual temperature, residual pressures, and also the residual compressibility factor. So if you have the sum of specified compound that which is the same class or similar class for the corresponding states, so you can see from the charts or you can take as the similar properties. So this is what we use the corresponding state. So which the state is similar, like let's say the reduced temperature, reduced pressure for argon, they are similar with the helium. So you can use the properties, argon properties to represent the helium properties. So this is, we call it corresponding state. And then the other, we have the phase equilibrium of the pure fluid. So this is interesting. When you say phase equilibrium, like we discussed before about critical points, this is, we call it phase equilibrium. So when you say phase, you have the vapor, liquid, or the solid. Equilibrium itself, it means balance. So when you discuss about phase equilibrium, it's actually like phase balance. For example, we have in thermodynamics many kinds of the phase equilibria. For example, like the vapor-liquid equilibria, liquid-liquid equilibria, solid-liquid equilibria, vapor-solid equilibria, vapor-liquid-liquid equilibria, or vapor-liquid-liquid solid equilibria. So it's very wide. So what's the function of the phase equilibria itself, and why do you need to learn about the phase equilibria? So if you're supposed to be, would like to, I can say in here, because we are process engineer, yeah, chemical engineering, they are process engineer. So in the end, you will optimize the process of in the raw, for the raw materials, yeah, in the large plant. So I take one unit in here. For example, distillations. I believe all of you know distillation. If you're supposed to be not sure what distillation is, so I can explain a little bit. So distillation is kind of the unit if you would like to separate volatile compound from the mixtures. So you can use normally relative volatility, or you can say alpha. So this alpha we can we use to optimize the to check like which one the phase or which one the compound it's easy to evaporate, which the compound it's less evaporate. So how you separate one mixture or one single phase into uh, two different compound. For example, if I have a binary compound, yeah, you would like to separate A and B, and based on the volatility, you can increase the temperature, you can play with the pressures, and then you will separate A and B from the mixture, so each of the compound. So in this case, you need to know the best operating condition. We cannot operate as in the critical point, like we mentioned before. That critical point, you cannot distinguish it between each phase, like between the vapor and the liquid phase. They are totally cannot separate. You cannot see even like the between the different phase. It's totally like half. So I have the video actually about the critical points. So if you interest, you can visit my lab, and then we can see like exactly like how the phase is. So you have bubble, you have dew, and then you have the critical. So for distillation, you should operate in the bubble point, because you will boil the liquid, and then the vapor phase will go to the condenser to condense and to produce the product, and the other it's in the reboiler. The less volatility, they will stay in the bottom, yeah, because they cannot evaporate. So here you need the phase equilibria of the pure fluids, especially if you have two compounds, you need the spatial phase equilibria of the two liquids. So each of, like if you suppose have the single or the pure fluid, it means one component only, and then you have the binary compound, you have two compound, yeah, or binary system, yeah, you have two compound, and you have the ternary system, three compound, or quaternary, four component. So the phase equilibria is not similar, because each of the property, even it's for the CO2, pure CO2, when you mix with the CO2 and amine, they're totally different. So in this case, in thermodynamics, you need to know about the properties like a phase equilibria, like at the atmospheric pressures or even the high pressures. And so we have the vapor pressures. This is interesting, normally vapor pressures. What do you think about the vapor pressures? So if you're supposed to I give the easy example in home. Sometimes you will boil the water. Right. So the boil of the water you will conduct at 1 atm or atmospheric pressure. So once you have you boil the water, they start to boil. So the pressure of the water itself, we call it, this is the vapor pressures. So they will have the specific pressures and then the temperature, of course. So in this case, the vapor pressures mostly we conduct at the constant temperature or isothermal conditions. So another example, if you boil the water in the mountain, yeah, remember in the mountain you have the pressure is lower than in the normal atmospheric conditions. Yeah. So boil water in the 1 atm, you just need maybe 100 degrees C. But in the mountain, maybe 80 degrees C already, you can boil the water. So you can see that difference in here, that it's because of the different pressures. And then the temperature also difference. Remember that temperature, they are linear relationship with the pressures. When you increase the temperature, your pressures also increase. When your pressure is decreased, your temperature also decrease. So they are correlate each other. And then also we have the calculation of the thermodynamic properties of mixtures, like partial mole property or excess the property. So this case is normally we apply for to calculate like how the properties inside of your mixtures, like the partial molar is energy Gibbs. So you can calculate like this system is spontaneous or non-spontaneous, and you have also like excess properties for your system or your one total component, like how they have the additional energy, like the excess enthalpy, excess entropy. So later, like the excess property, we can calculate like how much the efficiency of your energy. And also we have the calculation of the phase equilibria properties for the mixtures, like VLE calculation, like we discussed before about phi phi. Phi phi method, it's mostly used in the high pressures. And then also we have the gamma phi method. Gamma phi method we use for the low up to the moderate pressure. So here you can see gamma, it's for the activity coefficients model, and the phi method is mostly we use the equations of states. Yeah, for example, like Reddick-Kwong, of Reddick-Kwong, Peng-Robinson. This is the phi method. So we can use the some figure in here, like this is the sketch. Yeah, like a course contents like what you going to learn in the one semester about thermodynamics. So when you discuss about thermodynamics, it's quite huge. It's overall you can calculate or we discuss or we learn in this one semester is just discuss about the classical thermodynamics. Classic. It means macroscopic. And then we have the other is static thermodynamics. This is microscopic. So what's the difference between these two? If I have one class, yeah, in the class, we have 40 boys and then 60 girls, for example. So I just calculate like how many boys and then how many girls inside the class. This is, we call it macroscopic. So overall, if you have one system, how much the material in or mass in and mass out, or energy in, energy out. This is macroscopic. So if you go to the static thermodynamics, this is microscopic. Don't worry, I will not going to teach the static thermodynamics for bachelor degree, but static thermodynamics or microscopic is mostly we conduct we learn in the 硕士, in the master degree or doctor degree or 博士. So they go for the static thermodynamics. So if I discuss about static thermodynamics, I will go detail, like how many boys have a tall 170 centimeter, 160 centimeters for the woman, and then how many peoples. And then I will take the probability, how the average tall in this class. So I will go details on the specific part. So this is, we call it microscopic. So if you go for the classical and then the static, they are normally cannot separate. For example, if we would like to calculate the efficiency, in this chapter we just discussed about classic. Mass in, mass out, energy in, energy out, and you can calculate the efficiency or how much energy you need, how much enthalpy you need. However, for the static thermodynamics, we're going to see that how the reaction occurs inside the system. I have the steam. I will check the steam quality, like is it my steam have react with the other compound, for example, or is it in the your equipment have two compound and then is it they have the reaction each other or not, how much the total energy that they consume. So what's the effect, why in the macroscopic you have higher enthalpy. So you need to go to the static thermodynamics, how the interaction between each chemical. So in classical thermodynamics, we will divide based on two. We have the continuum mechanics and three law of thermodynamics. We will learn in the chapter 2, 3, 4. And then for the thermodynamic property relationship, we will define as the pure and then the mixtures. The pure is the most interesting to learn before you learn about the mixtures, yeah, because mixtures you need to have different property on it. So for the pure, you need the pressure, you need the volume, you need the temperature, entropy. U for the internal energy, enthalpy, Helmholtz free energy, energy Gibbs free energy, and then phi. Yeah? So phi is coefficient fugacity here. So to check the quality of your your mixture, is it approach to the ideal, or they are totally like highly non-ideal. So here later we will discuss and departure properties. So this is in chapter 6 or 7. And also for the mixtures, we need to use the mixing rule. Suppose if I have two compound and then you will mix each other, so you need to know like how the mixing rule, or how the interaction between the like the compound A and compound B. So in this case, we need the mixing rule. So mixing rule, it's practically like the interaction between two compound. So I have for the equation of states, so we mostly use the mixing rule to calculate the total pressures, how much you need. So later we can discuss further for the mixing rule. Actually, like mixing rule, they have some technique how to calculate. So we will learn like step by step. And then another is Gibbs-Duham equations. Yeah, so we going to learn, and partial molar properties. So another side is static thermodynamics, microscopic. You have discrete quantum mechanics and statics mechanics. So like overall, these three kinds of the concept we just discussed about the probability. Like if you ever learn in senior high school about probability, yeah, like if you play the some kind of the chess, you have the white and black, and then how many times that you will get the white color or the black color. So this is discussed about the static thermodynamics. So the thermodynamics model we use normally like equation of states and corresponding states. Yeah, so you have the pressure function of the temperature and volume, and the Z here is compressibility factor, is a function temperature and the pressures. And also we have the activity coefficients model. You will have ln gamma function of the mole fractions or mass fraction here with the temperature. So we can calculate the excess property. So this static, it's a further, like after you learn macroscopic, and you will learn about the microscopic. So what's the application actually? So the application we can use for the process design. So we can calculate for the total work, total heat. Q is for the heat, and then eta is for the efficiency. So we will calculate in the chapter 3 and 4. So we learn more how to calculate the enthalpy, total of work, and then the Q, yeah, it's for the heat loss, or you have the heat inside your system. And then also we will these two application you will use in the process simulation. So later on you will study the process simulation in the end of your study, like I think it's in the 4th year if I'm not mistaken. So if you use Aspen Plus, this is one tools that we use for the process simulation. They will consist of two, yeah, properties and then the simulation. So simulations, it means like you design your power plant from the raw materials, how to produce the product. This is based on your simulations. Before you try to design your power plant, your plan, like what process, yeah, you need to know the properties, especially thermodynamics for your each component. Without properties, you cannot calculate for the process simulation. So please remember this course and try to learn about the thermodynamics. Try to like it, because you will use even you go to work. Yeah, so when you go to work, you not only let's say like, okay, like mostly like maybe one you study and then you think that it's done only in the school, but it's not. Actually, when you work, you will use the knowledge when you study in the bachelor, and then you try to apply in industry. I share one case, like when I was a process engineer previously working in the company, I used the many charts from the thermodynamics to see that my process is suitable or not. So that's in this contents, like we can learn like how to read the charts, and then later on when you go to the industry you will use this knowledge. And process simulations will divine or will calculate like how much the cost you need to convert the raw become the products. Another, we have the process analysis. So process analysis, we can divine that this process, it's actually it's able to conduct or not, is possible or is impossible. So we can normally calculate based on the mass balance, and then the energy balance and entropy balance. So these three concepts, it should be possible. If one concept they are impossible, so it means that your design it's impossible to conduct or to make, yeah, in the for the white plant process. And the other, we have the reactor analysis. So reactor analysis will discuss about the chemical equilibrium. So this mostly about the chemical engineering thermodynamics. So we discuss not only about the heat movings, but how the heat moving effect in the chemical engineering process. Because that's we are more interesting about the process, yeah, from the raw and then convert to the product. So we can have the product from our process. Then in here, I divide by two. One is heat and temperature. This is we call it thermo. And dynamics is motions. So actually heat motion or heat moving. So this is like roughly for the thermodynamics. So this is from the Greek, Greek language. So the thermodynamics, you have the flow of heat that produce mechanical energy that could be used in the industrial processes such as the steam engines, turbines, heat pumps, air conditioners. So in this case, if you see that flow of heat, like flow of heat, how much the enthalpy you need, and then to move your turbine, and they can then the turbine they can produce the energy or electricity. So this is the principle. For example, perhaps you ever hear about the geothermal energy. Geothermal. So we take the heat from the earth, and then we convert the heat itself. It's become like it's to move the turbine, yeah, turbine for the turbine blades, and they will produce or generates the electricity. So in this case, this is also, we call it flow of heat. So we convert the heat into the electricity. So you can use the steam engines or the and turbines, yeah. And the other is heat pumps. Heat pumps is mostly we use if you have like for example, if you stay in the country that they have the four seasons. I give example like US or perhaps in Europe. So they will use the heat pumps as to heat their home. So this heat pump they can use as the heater, and then also as the conditioner, as the AC, yeah, for the cooling. So if when summer, and then this heat pump can convert as the AC, or you can say lemchi, maybe it's for cooling summer. But if you supposed to be you have a winter, so this heat pump we can use the function as the heater to heat your rooms. So this is dual function. Like we will learn in chapter 5 about this. So heat pumps, how to read the curve for the heat pumps and how the efficiency for the heat pump itself. So, and we have the another, it was the history. Before we learn something, I think it's good to know like how the thermodynamics create before you go further. So actually, like in the 17th century, so 1911, yeah. So the one researcher at that time, they tried to produce the steam engine, but at that time they found that the steam engine the first time is inefficient. So why they say inefficient? because they only can convert 2% of the steam engines to produce the useful work, yeah, to generate the electricity. This is like at the time they're planning to generate electricity from the steam, but it's only 2%. Like at that time, because like they just care about the first law, and then they don't consider about the second law. And then at that time, like when the it's 2%, so what's happened in the engine? So in this case, like they need to use the prediction of the efficiency of the steam engine, because at that time the second law still not appear yet. Why I said the second law? Second law, it's the when you calculate entropy will be equal to the Q divided by T. This is in chapter 4. Later we will discuss further. So Q in here it means is the heat. Yeah, heat in the system divided by the total temperature. So the entropy will define like how efficient your systems in the for the engine. So at that time they in the industrial revolution, so the thermodynamics they don't concern about this law. And then 1849 the thermodynamics was coined by the Lord Kelvin. Yeah. So I believe that all of you know about Kelvin. So Kelvin that we use always in the each of the unit for the temperature, for the unit of the temperature, especially in the thermodynamics, we mostly use Kelvin. Yeah. So then he defined the thermodynamics at that time by the Kelvin 1849. Then Clausius found the entropy in 1850. So you can see like the gap. It's like from 17th century and then 1850 we found that the entropy. So at this time, like entropy, we can calculate the how much the Q or totally like the heat that can be generated in the system. So based on the entropy concept. And the Maxwell formulated the statistical mechanical branch thermodynamic in 1871. So because at that time the Rudolf Clausius they just consider about the macroscopic, like the classical thermodynamics. They don't concern like what happened, why our entropy is cannot increase, or perhaps like why our enthalpy is too large, why it's not cannot be decreased, or why we cannot control the enthalpy in our system. So this is we need to go to the statistical or microscopic thermodynamics. So James Maxwell they formulate at 1871 to understand deeply about the thermodynamics. So later, like if we discuss about entropy, please remember that entropy never decrease. Yeah, entropy is always increase. So if you go to the enthalpy can be increased, decreased, but for entropy is not, it's special. So this is later is in second law. We will learn like why the entropy never be negative. Entropy can be zero. It means that it's balanced, but entropy cannot be minus or decrease. So this is the concept that we should take care with. So later we discuss more about that, and then we have the Ludwig Boltzmann. This is the connected entropy and molecular motion. So 1875. I believe that you learn about the Boltzmann perhaps in the senior high school, yeah. So how to connect the entropy and the molecular motions? Because to be honest, like if you think about the molecular, they have their own velocity. So for example, I have two molecules and then this molecule is moving. Yeah. Like even like in surround of us. For example, like currently I was in the room and then you see that surround me, we have a lot of gas, particle gas, a small gas and bigger gas, but you just cannot see visualize because the gas is very small and then the molecule actually it's hit you, but because it's too fast you cannot feel it. And this is we call it that the molecular motion. So in 1875 we calculate the molecule, how the effect microscopic and then effect to the entropy. Then this is it means the scope for the history thermodynamics. So what you will learn for the thermodynamics, is it only for the chemical engineering? No. So thermodynamics is quite wide, yeah. So you can see that in here we have the chemistry, we have physics, we have geology, and then we have mechanical engineer, chemical engineer, materials engineer. So without the concept of the thermodynamics, we cannot control the process exactly. So for example, we want to uh, optimize our process. So you should know that how much the energy that you need for the process, even like for the material. You want to synthesize the material, why somehow is not stable or unstable stage, why, for example, like today we create the materials or we do the synthesize, let's say in here metal organic frameworks, and then tomorrow you synthesize the same recipe, you get the different results. This is mostly in research, you will see that this will happen. So what's the phenomena inside? So this is relates about the core of the fundamental core. So perhaps the thermodynamics, perhaps the reaction, perhaps we should control the, let's say, the mass transfers, like how we connect that the practical into to the core or into to the fundamental part. So in the end, all of the practical, you need the fundamental to explain the phenomena. So this is why we say that the thermodynamics, one of the core, it's important to learn. Then another example, I believe that thermodynamics also occur in the natural disaster. I give that example like volcanoes. You know volcanoes, right? I thought in the I just saw like last year we have the volcanoes in Indonesia. So at that time you see that how the process itself, like from the core of the earth, the excess heat, and then they will go up. So this is volcanoes heaven. Like hot springs in Peito, yeah, you go and then enjoy the hot spring. This is actually like from the heat moving. So heat moving for the hot spring from the mountain, and then they will flow to the some, let's say, basins, yeah. So here you can enjoy your hot springs, and also you have the plate tectonic convection. So this all is the heat, it's move. This is why we say that thermodynamics and natural disaster. And another, if you see that we have also typhoon. Typhoon. How the typhoons comes? Typhoon is actually is from the sea, like they are overheat and then produce a lot of wind, yeah. And this wind they will move and then go to the island. So is actually it's thermodynamics and occurred of and we have the natural disaster because of this. And the other is tsunami, yeah. Tsunami is also is kind of the one example. It's from the thermodynamics heat move because you have the plate tectonic convection and then they occurs the tsunami. So the wave from the sea they will go to the islands. So this one example how the thermodynamics is already happened in the natural phenomena. We have also applications geothermal energy. So geothermal energy, it's interesting. It's renewable energy. I believe that this energy we already expand in many countries. So what's the geo and thermal? If you discuss about these two words, is actually heat produced in the depth of the Earth's core. So in the Earth, yeah, if you have the in the Earth inside the Earth, you will produce some heat, and then this heat you can use to produce the electricity. So geothermal energy is basically is clean, and they are renewable resources that can be harnessed for the use as the heat and electricity. For example, here we have the production well. Yeah, you have the production well, and then this is pump. So they will go to here and come back to the earth. So they are actually is one cycle. So when they go to touch the heat exchanger, in the heat exchanger, we use the working fluid. So working fluid, it means kind of the chemical or fluids. Normally is a liquid phase. we use to move the turbine, and so turbine can produce the electricity in this case. So they will go to generator in the end. So in here the working fluid normally we use as the hydro HFC, hydrofluorocarbon. So this is also kind of the working fluids, or you use any kinds of the chemical, another chemical. So we can use for to moving to let the turbine move. Yeah. So when you have the heat from the earth, they will go to the heat exchanger. So in this case, heat exchanger. You know heat exchanger perhaps? Heat exchanger, heat exchange. Heat it means thermal, of course it's yeah. Exchanger it means exchange. So you exchange the heat, either the function to heat or cooling. This is heat exchanger. So in this case, the function is heating, because we want to absorb the heat from the heat of the earth, from the earth core. So you will absorb the heat from the earth, and then you will use to heating your working fluid. So then in the end, the steam will come back again into the injection wall. So they will come back again to the earth's core. This is, we call it, why the geothermal energy is renewable resource. So when you drill, actually when you drill on the earth's core, you will obtain many types, like oil. Yeah, you know how to production the oil also. Oil is from the earth, but the depth is we have the specific of the depth. So when you adjust the depth of in the earth, so you can produce the gas, you can produce the oil, you can produce the geothermal also. So everything it's from the earth's core. However, for the oil and then the gas, they are non-renewable resource. But for the geothermal energy, they are renewable, because you just consume the steam or heat from the earth, and then you reuse and come back again to the earth. Yeah, so for the working fluid here, they will go to drive the blades inside the turbine. So this is what we're going to learn later about each of turbine. You have the energy in, you have energy out. So you have T1, P1, V1. So here we have the temperature, pressure, volume, enthalpy, entropy, and then energy Gibbs. So this is the first condition. It means inlet, yeah. And then the second one, it was outlet. So then when you produce this turbine, so they will moving the blades in the turbine, and then they will produce W. So what is W? W, it means total work. So later, when you discuss work they define about two parts. One is soft work, the other is I can say that workforce, WF, WS. So they are totally different. So what's the difference between these two? So normally, it's based on the equation later is difference. If you check the unit, yeah, you got to know about your unit operations. For example, like any equipment that they can drive, they use the shaft. So this is, we call it shaft, is like kind of the kind of, you can imagine like pipe, then they connect with the blades. So this shaft will rotate your blades. This is, we call it shaft. So the work it's produced by the shaft process. This is, we call it shaft work. So like turbine, and then what else? The turbine, and then we have the pump, yeah, pump. And this is all is shaft work. And for the workforce, it's mostly about piston. If you know piston, piston is one of the unit that we use. For example, I give example like you have the bicycle in your home. Bicycle, when you push the tire, for example, your tire of your bicycle, it's you need to put some air inside. So you will use piston. Like normally piston, you will blew the air, go to the tire, so your tires become hard again. So this is piston. So the piston principle is just we don't use the software, but the total is based on the volume. Yeah. So you have the volume there, and then the pressure. So P delta V. Yeah, so in this case, like you have the volume and then you have the pressure inside. This is to calculate the work force. So later we will discuss further about the work and what's the function of this work. This work we will use to optimize the process. So how to optimize, how to reduce the work, more energy. Less work, less energy. More work, it's sorry, in this case, like I think if you discuss about this, it's depend on your function, yeah, your purpose. If you design, for example, like the work is to produce the electricity, is mean more work is better. Yeah, so it's depend on the production. So if you supposed to be like if you want to convert some energy, it's for the electricity, so it's better like if you have the more works. Yeah, more works is mechanical energy produced, it's better. So you have the optimizations process, you can optimize and then you can have the good efficiency for this process. Another, it was we have the basic principle for the thermodynamics. If you discuss thermodynamics, they consist of the system. So what's the meaning of the system, surroundings, and the boundary? So these three kinds of the concept you cannot forget. Please remember, because in the further chapter, maybe I just say system, adiabatic, close, isolated. So you already know what the definition is. So in this chapter, I will define what the system, what the surroundings, what's the boundary. So when you say about the surroundings, it means outside thermodynamic system. For example, I have the boundary here, dash line. Yeah, this dash line we call it boundary. It means the limit from inside and outside. What's the distinguish or difference between inside and then the outside? When the system is outside of this boundary, this is we call it surroundings. And then boundary itself, like the closed surface surrounding a system. So here the dash line, if you check that this dash line, this is all its boundary. So to distinguish outside and inside. So and then the specific region inside, it's inside of your system. Like you have the mass, you have the force, volume, and so on. So this is inside the system. This is we call it inside. Yeah, it's a system. Yeah, system itself. Like it's only in inside. So when you supposed to be, you have the. I can give you one example. Yeah. So if you have supposed to be let's say bottle, or you have a bottle. Yeah, bottle, you put the water. So the water inside your bottle, this is system. So the boundary itself is the bottle itself is boundary, and outside the bottle, this is surroundings. So please remember about this. And then system, they consist six kinds of the system. If you have in here, like we have the adiabatic system, we always assume like somehow when you have the problem, you need to know about the system is adiabatic, closed or open. So I hope you don't forget about the definitions. So adiabatic system, it means no heat flow. So in here I give you red color. It means to give you, to let you memorize that it's no heat flow, or totally like well insulated system. So in this system is mostly the Q is equal to B0. It's mass, yeah, because it's adiabatic, well insulated. It means no heat loss. And then maybe yes, we have the mechanical contact, but we don't have the heat flows. And the closed system, it means no mass flow. You can imagine it's closed. Yeah, close. You put the water, it's inside your bottle, it's full. You close. So it means no mass flow, no mass in. No, didn't have a mass go inside to your system. But for the energy flow, we have. We have energy in and energy out. For example, the easy way, we put the warm water in the bottle or hot water in the bottle. And you close, we don't have the mass in and mass out, yeah? But how about the energy? After you put like 2 hours, is it the temperature still warm or still hot again? It's not. Yeah. So it means that you have the energy in and energy out. Yeah. So in this case, this is we call it closed system. So later in the next chapter, when I say close, you can imagine that this is no mass flow, but you have energy in and energy on. So only energy flow. And the other is isolated system. Isolated. So it means that the system is totally isolated. Like 2019 we got COVID, yeah. We totally isolate. So it's mean we cannot go out. So in this case, mass in, mass out, you don't have mass in, you don't have you have perhaps like isolated is already like inside. So your system is only in inside. So you don't have mass flow, you don't have also energy flow. This is we call it isolated. So for the easy one, it's for the system. For example, like if you operate in the equilibrium cell, let's say, or in the, I can say, yeah, equilibrium cell. Equilibrium cell, like kind of the cell, you can imagine like a cylinder, isolated, you put the jacketed. Yeah, like our body, if we feel cold, we use the jacketed. In English also we call it jacketed. So this is, we call it isolate. So we don't keep the temperature go out. So we just keep the system inside. It should be, this is we call it, it's isolated system. And the other open system. Open, of course, open you have mass in, mass out, energy in, energy out. This is open. So they freely move. And the other we call it steady state system. Steady state, it means that the system doesn't change with the time. So they are stable. So they don't change over the time. This is, we call it steady state. So when you state later, when you saw that the thermodynamics problem, you should able to divine that this system is a steady state, this system is open, this system is closed. So the system that don't change over the time, this is, we call it steady. And then the cyclic system, it means one cycle. Yeah. So if you have the periodic path of the system, which has the same properties, this is, we call it cycle. So like before we discussed about the geothermal, so they have the heat in and then go out. This is, we call it cyclic, and come back again. So one cycle. Yeah, so this is the systems in thermodynamics. So please memorize and then please review about the systems before we go to the further. So the central problems, these problems is mostly happen in thermodynamics. So we have the principal thermodynamics. So principle is not only about the chemical, but also we learn about the physical phenomena. For example, I have reactor. So we not only discuss about the design of the reactor itself, but also we got to know about the chemical interactions happen or chemical reaction inside your system. Should we use the CSTR? CSTR is for the type of the reactor, like continuous start reactor tank, or you got to use the tubular. This is, we call it physical, but the chemical, it means also we have. And then if you also divide the physical and chemical, somehow we can have the definitions also. For example, like absorption process for the CO2 capture, yeah, because the CO2 capture is very hot topic. So I give example like physical. Physical, it means that in the interaction that easy to release. For example, I have the CO2 with some specific chemical compound, but the forces is just based on the physical. So they don't have chemical interactions. So the physical is easy to regenerate compared than the chemical phenomena. So this is also we can divide as the physical and chemical. And the macroscopic system is normally is about the average change in the system. So it's mostly large number. So it's not go to the micro, like we discussed before about micro state or microstatic. Yeah, this is micro. But macro, it means like it's overall. So it's large system. And the macroscopic, for example, like we have two types, like temperature and density. So the temperature, it means the extent of the molecular motion. So we have the molecular motions, and then you increase the temperature, you have the system, for example, water, yeah, you boil. So the water is become the gas phase and they will move, freely move. This is, we call it molecular motions. And density, it's measured about how closely your molecule each other in the package. For example, density of the liquid, yeah, they are mostly like dense compared than the gas. So if you supposed to be density of water, let's say one gram per centimeter cubic. For the gas, why is less than the liquid phase? Because the molecule in the liquid, it's more closely each other. So if you see in the microscopic states for the liquid phase, you will see that the molecule is actually like joined together. For example, I sit here, I have my neighbor. We just close each other. This is, we call it closely packed. But if for the gas, they are freely moving. One here, the other go to the other side, yeah. So they are freely like random. So that's the density of the gases is practically like less than the liquid phase. So in the total energy or the thermodynamics, we have three types of the energy. I believe you remember in the senior high school, you always remember about the potential energy, kinetic energy. So here I will add one, internal energy. So internal energy, we will discuss about the motions of the atoms. So don't think that the atoms didn't have the motion. So they have the motion, of course. For example, like we have the molecule, even like I give you example, like surround me, we have a lot of the gas. And then because the velocity is quite fast and then they are very small, so we cannot see by our eyes. And then if you go like each of the gas, they are random in everywhere. So they have the motion in each of the atoms. So they have the electronic, nuclear, vibration, and rotation. So the molecule itself, they can rotate or they can vibrate, yeah, and touch their neighbor. Like for example, if you have the heat moving, let's say like you can touch your friend, even like, hey, and let's move the heat. It's like this, like the way how to move the heat. It's based on the vibration, rotation, and then the nuclear and electronic. And potential. Potential in here because of different of the high. Yeah? So you have the potential energy. For example, I have the turbine in the first point, and then I would like the tank. And let's say the tank here, the first point is tank, and the second point another tank. So you have the elevation, the different height. This is, we call it potential. And you have the kinetic energy. Kinetic is based on the velocity itself, like energy, translations, and then how about the motions of the molecule itself. I have the velocity, the first velocity, the first molecule. So I have the velocity maybe 2 meter per second, and the other is 1 meter per second. In the end, like they will touch each other. So in this case, we can say that this is mass of molecules or motions, yeah, molecule of motion, because molecule they are moving. And all of these three energy, this is, we call it total energy. This is what we want to discuss, total enthalpy, total energy, because energy later we relate about cost, yeah, about funding, yeah. For example, I have 1 giga, or let's say that 1 gigajoule, yeah? And then with 1 joule, of course, is the 1 joule is more cheaper compared than 1 gigajoule. In the end, you need the electricity, even for the heat exchanger, yeah, to heating, we need to have the energy consumption. So that's why the total energy try to reduce the efficiency. Another is we have the state. State, it means conditions. So the state is regarding about the properties like rho, the rho, it means density, the temperature, the pressure, mole fraction, and so on. And another is phase. So which kind of the phase that you would like to transfer? So for example, here I have a liquid phase. Oh, I have a solid phase. I have a gas phase. So these three phase is different. Even the properties is not similar. And the constraints in here you can define in thermodynamics. I want to operate constant pressures. or I want to control the temperature. So it's constant T, but the pressure will change. This is, we call it constraint. That's why in thermodynamics we have isobaric. Isobaric, it means your pressure is similar. So P1 equal to P2, P in equal to P out. So you control the pressures. Isothermal, this is, we call it, the temperature is the same. T1 equal to T2 equal to the T. And then the other is isochoric. Isochoric, it means the volume. Volume, it's constant. V1 equal to the V2 equal to the V. Yeah, so this is, we call it iso. Iso is Greek letters. It means same. So another is, you can say that isentropic. Isentropic, it means entropy similar. S1 equal to the S2. Entropy similar. Enthalpy, isenthalpic. Isenthalpic, H1 equal to the H2. Yeah, so there is many kinds of the constraint that you can control in the thermodynamics. Okay, so here we have the typically general interest, yeah, for the thermodynamics problem. So we have energy problems here. You have the state 1, and then we want to produce the state 2. So normally, thermodynamics just regarding about the conditions. Condition 1, go to the condition 2. So how the efficiency, you would like to change the energy from state 1 to state 2. So this is, we calculate the H1, T2, H2, and then you have the G1, you have the G2, T2, P2, yeah. The same with the turbine. Like here, turbine, you have the in and out, yeah, the same. And then with the heat engine also the same. So you have in, you have out, and this is perhaps is Q, perhaps is W, sorry, W. Here also you have the W. So in this case, like you need to know about energy flow problems. So what we're going to calculate later about here, like you need to know the total energy required, efficiency your systems, and we can calculate like how much the efficiency actual that you need to solve your problem. So please remember that when you solve the thermodynamics problem, you solve the questions. Try to draw sketch. I don't mind that the sketch is beautiful or not. However, when you draw the sketch, it means that you can understand the concept of the what you're going to calculate in the system. Yeah, so once you saw the questions, so try to figure out in the sketch. It will helpful for you. For example, here we have turbine. So you can have the icon of the turbine and then in and out. So it will be helpful to calculate. So it's more clearly. So please don't forget always sketch. This is the first step. And divine or assume is based on the system like open, close, or they are adiabatic. Which one you should negligible? Maybe the potential, perhaps the kinetic you can negligible. So it's depend on the assumption. So we have the equilibrium thermodynamics problem. So equilibrium thermodynamics problem, we need the identification or prediction. For example, here we have the equilibrium state. We have the pressure, we have the temperature, we have the mole fraction I. So I have two kinds of the pure compound. I have here ethanol with perhaps here the methanol. So I want to mix each other or ethanol and water. And then you will see like, is it I divine two phase or one phase? So it's not every phase, even though they are liquid, they can dissolve each other. For example, I have the water and I have the oil. When you mix, did they become one phase? No. They are two phase because the oil cannot totally miscible. Miscible, it means mix with the water. But if you mix ethanol and water, they are totally single liquid mixture because they are miscible, yeah, miscible compound. And how the prediction of the equilibrium state, how long you achieve the equilibrium states, and this is about the time. That's why when you do the experiment for the phase equilibria, you will need more time to achieve your equilibrium state. So perhaps 1 hour, perhaps is 2 hour. We never know about the how long you can achieve the equilibrium states. So when you say equilibrium, it means balance. And we have the chemical kinetics inside heat or mass transfer, fluid mechanics. How fast your system? Is it maybe in 1 hour they already reach the equilibrium or not? So for sharing, when I did the experiment before, I have one system, they achieve the equilibrium is 14 days. So 2 weeks, I only can get one data. And the same like hydrate. Hydrate system, hydrate, it means that the new fancy technology to storage the gas in the ice. So if you have the ice, water like ice, you put or you storage the gas inside the ice. So this is we call it hydrate. So in the future, you will saw that we can storage the gas. Is just best use the ice, one ice, and then you burn, and then this is one of the fancy technology. Yeah. So this hydrate we did experiments. 1 year is one curve only. So it takes time. It's not fast like you can get the achievement prediction of the equilibrium states. So we have the chemical kinetics and heat or mass transfer, fluid mechanics, and then how fast your system will respond a change. When you decrease the temperature, like how fast your systems can um, decrease or the can change, yeah, can change to the other state. So this is we call it the equilibrium. And then you have the systems of unit. This is mostly that we use like basic units and derived units. So you have length, mass, time, and so on. So I believe that you know the SI, yeah? Systeme International the United. And then also you have force, energy, pressure, power, frequency, and mass, density, and volume. So here we practically use in the thermodynamics. So make sure write clearly of the unit. So each of when you solve the problems, you need to define the unit in each of the concept. Yeah, for example, like what unit you use. So SI, then use it should be consistent in SI. So if you use British and then use the British. So another, it was the just recall like for the SI unit. So you have the tera, giga, and so on. Yeah, I believe that this is you already know about the prefix for the SI units. But please remember, write clearly for the units. And we go to the equilibrium state. So equilibrium state, when you say that equilibrium, there is some steps like we have this figure. We have these three dots. Yeah, one is metastable. This is time invariant. So these two metastable, it means that the condition that they will approach to the equilibrium cell, to the equilibrium condition. So for example, like I have 0.1, but somehow when I do the experiments, like you still between like 0.7 or to 0.1. So in the between, like they try to approach to the equilibrium until when you repeat several times and then you get the exact value. So the equilibrium, it's and the metastable, it's their time invariant. It means I did the experiments today and I would like to measure tomorrow. The result will be the same because your system is already reached to the equilibrium. So this is we call it time didn't change with the time. So time invariant. So but if your system still the unstable of course is depend on the time, yeah, because they will change like vary with the time. So when you state equilibrium, it means doesn't vary with time, uniform. It means no internal temperature, pressure, and then volume or concentration gradient. So all of the system, if you have the one system, you measure in this point, go to the others, so it will be the same. So they will not totally change. So this is we call it uniform. And all flows like heat, mass, or work, it's equal to 0 in the system. So it means that no gradient. Yeah. And the net rate for the all chemical reaction, it's equal to be 0. So how about the equilibrium non-driven the system or driving force? It's 0. So this is also one of the criteria. Yeah? it should be driving force is equal to be 0. It means you don't have the heat flow, you don't have mass flow, you don't have a momentum or flux or momentum or velocity gradient. So all driving force, it should be equal to be 0. And then here we have the two kinds difference definition. You have natural flow, you have the force flow. So natural flows, it means arise naturally and driven the system to reach the equilibrium. For example, I have, if you know the heat, the heat you have convection. For example, I have the logam that I put in the oven. Coin, let's say coin, Coin I put in the oven and you feel like it's heat. You put in the outside. After you take it out from the oven, you put in the atmospheric condition. Maybe after 1 hour you touch, it's not hot again. So this is, we call it naturally. Naturally, it's driven to the system to reach equilibrium. So the naturally heat on the surface of the coin after several times, and then the temperature will similar with the surrounds. So this is, we call it natural rise, or the system they driven to reach the equilibrium. So in the end, the temperature in the coin, it will be equal with the temperature in the surround. If the force flows is the flows imposed on the system by its surroundings. So in this case, it means that when you have the system, for example, I would like to let the coin temperature faster. So I will use a fan, to let the temperature moving fast. This is, we call it force flows. So I use the external works to let the coin cooling down. So this is, it means force flows. Then we have also in thermodynamics stable and unstable. So when you discuss about the stable, it means I move the cubic state, Whenever they go already stable, the system will return to its initial equilibrium states. So for example, I move this yellow and then the green one. I move a little bit, so it's become unstable. But it's fast to come back again to the initial position. So this is, we call it stable. But if unstable, you put in the initially unstable condition, they will not return into the initial state or into the stable condition. This is unstable condition. So for example, like subcooled liquid tapping on the side of the containing vessel, so will cause the liquid to freeze. So this is, we call it unstable. The same, for the natural process, is mostly like the system, they are evolved toward an equilibrium state. So equilibrium state, they are mostly like stable states. But before they reach to the stable condition, they start with the unstable. That's why in the engineering, you learn about steady state and unsteady state. For example, if I have the process first, like kind of the process, and the first state, it's unstable, like they have disturbance, up, down, up, down. If you see like, what's the easy example, like I can give like the current. If you ever measure the current in electrical or any current, so the process, like first time you open the system, the current will up down. So until at some point they will reach to the stable. So this is, we call it the equilibrium states. And we can discuss about what's the important characteristic inside the thermodynamics that you need to know. We have the pressure, temperature, equilibrium. So in this case, what's kind of the measurable properties that we can use? Normally, it's not pressure, temperature only. You have the third, it was volume. For example, if you would like to measure the pressure, you can use the pressure gauge. Pressure gauge or any kinds of the pressure indicator. Like manometer, also this is pressure indicator. The same like the temperature, we can use the thermocouple or the resistance temperature detector, or you can use the thermometer. If you supposed to be feel unwell in your body, you use the thermometer. So in this case, this all is measurable. And volume, you can use the volume 1 liter, 2 liter. This is measurable. So we can control these three normally in the system. For example, I have here A and B. So A and B, this is kinds of pistons. In the middle, they have some system that they are easily flow. Go to the right, left, so they are freely, like friction less, yeah. So we don't have friction in here. So to calculate, normally like for the piston, we have the pressure inside. So the pressure we can calculate by the total force divided by the area. Yeah, so you have the total force inside your piston and then the area of your piston itself. So F in the physics, yeah, you have the mass multiplied by the gravity force and then divided by the A. So the pressure is normally is evident. So you can use device that the change in some indicator like position, the height of column, of electrical properties, so you can calculate the pressures. One example, for the A and B, we can define the total pressure. So remember, this is mostly like you will miss when you do the experiment, especially. When you calculate the pressure absolute, yeah, don't forget calculate plus P atmospheric. Because when you supposed to be, you measure in the system. You have this one system and then you would like to measure the pressure inside of your system. And you use pressure indicator. This is pressure gauge. Pressure when you measure this is pressure gauge from the equipment, yeah. And then if you would like to convert to the pressure absolute, you need to plus pressure atmospheric. So please don't forget this. This is somehow simple, but we miss. Pressure absolute equal to the pressure gauge plus PATM. So the temperature is defined like the system property, which indicates the system are in thermal equilibrium or thermal contact. For example, we can calculate here based on the experiment, PV equal to the A plus R tau. So in this case, if you supposed to be remember about ideal gas law, PV equal to the RT, yeah. So the temperature we can divide by the tau plus A divided by R. So in the A itself, it was and the tau, it was the sum constanta from the experiment results, yeah. So you can prove like actually like the ideal gas law is correct, PV equal to the RT. So if you ask me like, teacher, is it possible in the real that you have ideal gas? Yes. One example, ideal gas, it's happen when you have very low pressures in the vacuum pump. If you saw that in the vacuum pump, yeah, Changkong, yeah, maybe the vacuum pump. I think the vacuum pump we always use to remove the impurity inside the system. So the vacuum pump itself, it means that if you would like to remove the impurities and then you want to see that how ideal it is, the pressure or the molecule in the vacuum pump, like let's say the total pressure is minus 0.7 or is go to the minus. So it's very, very low pressure. So it means that no interaction between each of the gas. So this is, we call it, it's ideal gas law. But if you ask me like pressure in the surround us, yeah, we breathe and then in the air, this is ideal gas? No, it's not ideal. Because if you check like pressure, in the senior high school, we always assume pressure 1 atm and then this is some assume that is ideal gas law. But actually, if you go through the interaction, it's not ideal. Like the surround us here, we have a lot of gas. We cannot see. But they have the attraction, they have repulsion. So what is this? Attraction, it means when the negative charge meet the positive charge. So they will attract each other. This is attraction force. When they are repulsion, it means negative with negative or positive with positive. They will repulse. So like you play with the ball or something, you will touch each other and then they will repulse. So they are even 1 ATM, they are non-ideal because they have attraction and they have repulsions. So this is the difference. But for the pressure, it's very low. It's under vacuum pump. Of course, this is ideal. So it means that they don't have interaction. Maybe one in here, the other go to the other side. So each molecule, they are diverse and they don't have the interaction each other. So this is, we call it ideal. When you call it real, they have interaction. So if you have the pressure in here, yeah, since the pressure, so your volume, it should be larger than zero. Of course, the temperature is larger than zero. From the ideal gas, you can see like when you have the pressure, your V and T cannot be zero, yeah, of course. So you have in here, it means that the volume is normally 22.4, yeah, and then the temperature for the ideal gas, yeah. So in this case, we can go, how about the temperature scale? So the temperature scale, this is the old or traditional way. So you can use like open up atmospheric, and then they will have the gas bulb in here. This is in the blue one, in the blue points, like the arrow here. This is idential points. So we can calculate the gas constants based on this. So the gas constant actually, it's necessary to calculate, like if you use the pressure like ideal gas law, yeah, you have the R, and in some cases also we need the gas constant to calculate. So for example, here you have the how to calculate the gas constant. So PV in here we have the B. It means when the water it start have the boiling points, and then the F in here when the water is start from the ice points and divide by 100. So actually this is similar like when you want to calibrate thermometer calibrations, you put your thermometer into the hot water and you check is it 100 or not. If not 100, it means broken, yeah. And then when you put in the ice, is it zero or not? So this is how we calibrate the equipment. So when you have the equipment, whether it's new or old, you need to calibrate every time you did the experiment. So this is better because to check the accuracy, is it your equipment is working well or not? So this is the gas constant. You have different kind of unit, so we can revert depends on which kind of unit you use. So you can choose one of these. Then we have the thermometers here. You will divide ideal gas thermometer. For example, here T, it's in relationship, linear in relationship with the PV. Yeah, it's true, like from the ideal gas law. So for the mercury thermometer, they will depend on the specific volume of the liquid mercury. So if you check long time ago, they have traditional way. So they have the mercury inside, and then you will calculate depend on the elevation of your mercury, and then you calculate the how much the temperature. I'm not sure right now. We still have this. I think we still have, yeah. It's easy to find the mercury thermometer. And then you have the other platinum thermometer, yeah. This is mostly use the electrical resistance of the platinum wire. So this is a highly accurate, yeah, platinum thermometer. So depend on the electrical resistance. So based on the thermometer is practically like this. So you have the open, so they will keep open, and then based on the elevation or based on the electrical resistance, you can calculate we can define the uh, thermal, or how much the temperature in the systems. Then we have the heat work and the conversions of energy. So here it's the definitions each of. So I will put like in the chapter 1 all the definitions. So in the another chapter is the rest is calculation. So please review and then please recall. So the temperature is related to the internal energy. So remember before we discussed about the molecule motions, the translation energy, and then this is all is about the internal energy. So the internal energy is basically about U. In thermodynamics, they have the concept is U. U, it means is internal energy, and that depends on the temperature. And heat, it means that the transfer energy at the T difference. For example, I want to transfer the heat, yeah. Heat naturally, they will flow from the high temperature, go to the low temperature. Yeah, like we just discussed about the coin, and then you put from the oven, you take it out. So this temperature, they will transfer the energy from the coin itself from the hot temperature into the surrounding. So surrounding, of course, is lower. That means driving force. We discussed before driving force, yeah? Remember that each of the transfer, they should have driving force. That's why in natural, you always have the high concentration go to the low concentration. High temperature go to the low temperature. High pressure, they go to the low pressure. This is all is driving force. And driving force divided by the resistance. Yeah, resistance in here is distance. For example, I want to transfer from the first point go to the second point. So I need to know the distance. So it means driving force divided by the distance. This is we say transfer, either energy or any kinds of the mass, yeah, or concentration is similar concept. And the work itself is transfer energy by the mechanism that involve mechanical motions, like we say shaft, yeah. So you have driving, like the driving force from the, you have the shaft and then with the blood in here, so you have the shaft work. So they will convert the mechanical motion into to the work, yeah. So in here we have the total energy, internal energy plus potential energy plus kinetic energy. So the internal energy, it means change when the external forces result is deform. Deform, it means break, yeah, deformation. When you have this system and then they will expand or enlarge, extend, this is we call it deformation of the system boundaries. And the potential energy, kinetic energy, is changed with the result of the motion without deform the boundaries. So in the internal, they change, they, for example, like piston, yeah, they are flexible moving. So from the short space into to the large space, they will deform in the system. But for the potential and kinetic, they don't deform in the system. They just, let's say like for the short system, and then you have the kinetic and the potential, so they will not change even the deformations of the system and movement of the solid body from the external forces. So the energy system increase, yeah. So the energy system will increase, for example, like supply the electrical energy. So the electrical energy is can be formed from the mechanical energy, like turbine, they can produce the electrical energy. So this is one example. And we have energy and first law of thermodynamics. Okay, so before I discuss about the energy and the first law of thermodynamics, so what is the molecule motion? So for example, we have in here the first box here in the left, like we have T1, and then you see that the red, it was the atom, and they move each other. And then when you add heat, the particle is mostly like freely move, molecular motion. So it's become like T2. So the first law defines is energy, about energy. The system can be considered as a sum of the internal energy, kinetic energy, and potential energy. So you can say that the energy cannot be destroyed, yeah, but energy can transform from the one form into the another form. This is the first law of the thermodynamics. So actually, it's delta E equal to the Q minus W. So delta E itself can be from the thermal energy, kinetic, and potential, and so on. But mostly kinetic, potential, they will remain as constant. So in this chapter, we just assume that kinetic potential is constant if in the question didn't give you specific velocity. But if they give, for example, there is one questions later that the velocity is not constant. So the velocity, for example, the t in the input and the output is totally different. So you need to consider, of course, the kinetic. But if in the question didn't give you the specific velocity or the potential, you don't need to consider these two. So you just consider about the thermal energy. So we can calculate here like by the Q minus W. So Q is heat input in the system, and then W is work done by the system. This is what the key, like you need to know the equipment, and then you can define this is the soft work or this is the workforce. Is W in here, we write it's general. It can be used, the soft work, it can be used for the workforce. So later you need to know about the system, and then we can assume according to the system itself. Then we have the second law, entropy and second law. So the entropy, it means that the extensive the scalar property. Yeah. So the entropy, it's of the thermally insulated system. They cannot decrease, and it's constant if and only if all process is reversible. It means if you have reaction A go to the B, they can come back B go to the A. This is, we call it reversible. So they can go to the right side can go to the left side, come back to the initial state. So this is, we call it reversible. So when you saw later in chapter 4, the S, when they say that reversible, it means the S generation, it's equal to B0. Because entropy, they always increase, so they will produce the generation. So in this case, if they are reversible, it's equal to B0. But if they are irreversible, so you will have the S generation. So you cannot neglect. So you need to sketch, assume, and then state each of the equation that you want to use. So your assumption and your equation, it should be relates. It should be consistent. What your assumption and then your your equation divine definition, it should be consistent. For example, here you have the process like we have the things, yeah, on the surface, and then I want to move with the specific of the force, and then we can calculate the S or entropy here. So the entropy in and entropy out, how much the difference. The same with here, yeah, we have the systems, and then we want to mix, and you can see that in here like how the scalar properties of the S properties. In this case, like, is it the system is increasing or is decreasing? Also, we can concern. Remember second law, the entropy never decrease, they always increase. The same like I can give you example. For example, our Earth, our world right now, it's getting old, yeah, yeah, because it's by the time they will increase. They never come back to the 1910 or you can see like the iceberg. Currently, like global warming is melting, and this is change because the entropy is change. They will never come back to the 17th century. So this is why we say that the entropy and second law thermodynamics, they always increase, never decrease. But they can be constant or they can be S equal to B0. And the other is Joule's experiment. This is about the mechanical like observations about the amount of energy. So we always use like for the work, yeah, or 1 joule, or for the energy mechanical work and electrical work, or 1 watt per second. So he did the experiments. I think in your textbook, I used the textbook. It's Sandler. You can freely take a look like this Sandler about principle of chemical, biochemical, and engineering thermodynamics. So they have consist table 151. This is kind of the experiment to prove that the equivalence of the heat and work. And you can see like the experiment, he designed many kinds of the experiment design until he get the conversions like 1 joule equal to the 1 Newton meter and 1 joule equal to the 1 watt per second. So the same for the thermal energy is also design energy in form the internal energy and heat. So like we calculate before, yeah, the Q minus W delta E equal to the Q minus W. So in here, like delta E, it means consists of the internal energy. So then you have the Q, it's for the heat, and then minus the total work. So the mechanical energy, it's a work itself. So that's why this is one of the previous about the thermodynamics, like how we calculate, and then how about the unit conversion. So in this case, please memorize that the conversion, it's important. So when you solve the problem, for example, like in here you use SI and then in the end you use British. This is not similar. So you need to use, if you want to solve the question asked about the British, and then just use the British for the whole of the system. So conversion unit is the most important. And then we have here like about the specification of the equilibrium state, yeah. when we say that before about the stable equilibrium, is characterized only by equilibrium properties of the system. For example, equilibrium properties like pressure, temperature, and the volume. And we conduct the experiment until the specific time, until you reach the equilibrium. So, according to you, there is have the pressure, volume, temperature, and energy in this case. So, which one is extensive, which one is intensive? So, these two definition is different. One is the size independent, the other is size dependent. So, I believe that you're curious about that. So, we have the intensive variable here, which we discuss size independent property. So, size independent property, it doesn't matter how much you put 1 liter or 10 liter, the temperature and the pressure, if they are similar, is the same. T1 equal to T2, P1 equal to P2. But extensive variable, it means that depend on the size. For example, I have 1 kilogram and 2 kilogram. It's different, like mass and the volume. This is or total energy. This is extensive variable. I put 10 liter. The total energy, of course, different with 2 liter. This is extensive variable. So if you have the similar properties like 1 kilogram nitrogen, you have T1, P1, V1, M1. Yeah, similar. Yellow, I have two kinds of the gas. One kind of the gas, but two cylinder. And then I would like to mix this gas. So of course they have the 2 kilogram N2, but the property they have T2, P2, V2, and M2. So in this case, like this is, we call it like extensive variable. The total energy is large, and then the mass and the volume, they are increasing. So how about the stat and pet variables? Okay, so this one is interesting. Please memorize also, because in chapter 3, you will saw that one question about how to prove the state and pet variable. I hope you understand the definition. The state variable, it was pet independent. It means that I want to go for the A, for example, and then from the A, I want to go to the B states, yeah? So I have two ways. One is the orange line, the other is the green line. So when we discuss about state variable or pet independent, it doesn't matter which way. I go to the which orange or I go to the green, the result will be similar. So the value of any state's variable depends only on the equilibrium of the system. So we don't care about the path we go, like orange or go to the green. The destination is the same, go to the B. So this is state variable. For example, what's the state variable example? We have internal energy. We have entropy. This is state variable. Another, we have path variable. It means depend on the path or depend on the path of change or work, heat. This is one example. For example, like we go to the green or orange, the effort is perhaps is different because how to calculate depend on the pressure and the volume change. So here, the under area of this curve, this is total of work. So the path A and the path B is different effort. So in this case, we can categorize as the path variable. So equation of states. Once after we discuss about equilibrium, we discuss about the path. We have another is equation of states. So what's the equation of this? So equation is just to help you to describe that these systems can be calculated by the equation. For example, I have the one data. Data is means like data. You have a lot of data. But how to simplify your data? Of course, for example, I have the data 10 to 0. And then I want to measure the 4, but I don't have the data. Yeah, I don't have data about this, but I want to calculate for number 4. I have 0 to 10. How you calculate number 4 if you don't have the experimental data? So we need some equation that can represent for the interpolations of your system. So 0 to 10, you can represent based on the equations that can help you to calculate some points that you don't have the original data, but you can describe that this system based on the equation. So we call it equation of states in here because you have two types. One is volumetric and then the other is thermal. Mostly we use the volumetric equation of states because pressure in here I use the cap, cap in here, they have different definitions in thermodynamics. It means that you have the unit is based on the mass. If I put V underline, this is for the molar, this is for the mass. So remember, if the unit use the head, it means that it's mass property. But if they use the underline, it means molar property. So please remember this. That's why sometimes in thermodynamics, if you forgot to write the underline and then the cap, this is need to change. This mistake cannot be happen because this definition is different. V cap, V underline. This is the most important. So why the pressure and the temperature we don't have cap and then we don't have the underline? Because this is not unit. It doesn't matter about the size, right? We call it intensive property. So the pressure and the temperature is intensive property. It's not extensive. It doesn't matter with the mass. Mass and molar, it means that the unit that depend on the size. So that's why they don't use the cap. So the pressure, the temperature, it's all V. We can use the equipment to measure. And thermal equation of state, they use the internal energy and then the volume, for the volume and the T. U and V, it's the size dependent, but it's not with the T. However, in the application, we seldom use the thermal equation of states. The reason is how you calculate the U. Can you calculate the U? It's hard to measure. We can calculate the U, but we cannot measure the U. For example, we don't have the specific equipment to measure the U. We can calculate, but for the U, internal energy is not applicable. So it's mostly easy to measure the P, V, and T, use the pressure, volume, and the temperature, volumetric equation of states. Okay, so in thermodynamics, we always use this, P, like brackets T with V, this is equation 1 and equation 2. One is function of the TP and the other is PV. So what's the difference between this? It depends on the function, So it means that, for example, I have 1 equal to 1 bar. So which specific temperature that I got 1 bar, this one? Is it depend on the temperature and the V, depend on so the brackets, it means the function of the T and V, and then it's depend on the specific T and then P, and here P and V. So if you're supposed to be in equation 2, you see like U, T, P, and V. So P is actually like if they are equal, it means that U is equal to the UTV. So you can simplify like that. So this is for the this function. So in the thermodynamics, you will see many brackets like that. Then I give the definition here. Equation 1, the pressure is function, the temperature and volume per unit mass, And UTP, equation 2, internal energy is function of the PV, pressure and volume. So if the UPV, for the UTP is function of the temperature and then the pressure. So if you have ideal gas, U is function of the T. This is interesting, when they say that ideal gas, so because the pressure is actually like is less, so you can see that U and the cap is equal to the VT. It means function of the T. And it means when you increase the temperature and decrease the temperature, your internal energy consumption is different. And then if you have here like incompressible liquid, it means that your volume is not function of the pressure, but they are function of the temperature. So in this case, incompressible. Compress, it means you can change the phase, or like compressible, it means you can change the pressure. They are function of the pressure. But for the liquid phase, they are in function of the pressure. And for the gas, we can avoid to use the U and the T because for the gas phase, it's compressible. So they are function of the pressures. And then for the liquids and solid, we can avoid use the volume and then the temperature, because incompressible liquid, the volume is function of the T, so it's not easy to control. So non-equilibrium system, they are function of the time. Of course, because they are varied with the time, yeah. And local equilibrium means that non-equilibrium flows with a very slow system change in the perceptible rate. So the change of the flow, it is very slow. This is, we call it local equilibrium. Then the others, we have the important observation here. Remember that in any change of the states, like V dot nuclear reaction, the total mass, total momentum, total energy, like the internal energy, energy potential, energy kinetic, heat, and then work, they are conserved. Yeah, so remember the first law of thermodynamics. Energy cannot be destroyed, but energy can be created, or they can be changed to the other one form to the other form. This is the first law. So if you're supposed to be have energy, for example, like you put the 100 joule, but in the end it's not equal to 100 joule. It means that you have the energy loss. Yeah, so it's much you have the heat loss, but it's not disappear. Yeah, and then thermal energy and mechanical energy, they are actually quantitatively equivalent, and the quality of mechanical energy is larger than the thermal energy. So when you convert the work, it's more easily compared than you convert the heat. Why? For example, I have the system like in the cylinder. You want to convert like the steam engine, like the previously, yeah. It's not easy you convert the heat into to the work because you need to keep your heat. It's no loss, no heat loss. So it should be like it should be constant for the temperature. But for the work, you can transform this heat into to the mechanical energy to drive the turbine, and they can produce the electricity. And the time invariant states with uniform or composed of uniform subsystem, this is, we call it equilibrium states. And the equilibrium system will never spontan. Yeah, remember that you need to have the energy, then they cannot spontan for the system. So they are non-spontan. So the equilibrium states that arise naturally stable to the small disturbance. So this is for the equilibrium. And for the single phase, one compound, only to state variable we need to fix. Yeah, this is degree of freedom. If you still remember, F, it means degree of freedom equal to the total compound minus phase plus 2. So if you have the compound, it's equal to 1. And then single system, it means you have 2 degree of freedoms. So 2 degree of freedom in here, you can fix either this is the temperature you want to fix, the pressure, or the temperature with the mole fractions. So the rest you can get the other data. So one extensive property is fixed, its size, yeah. So this case, we summarize our important experiments, and other, it was the local equilibrium for the non-equilibrium processes. If the internal, they have a rapid with the respect to the rate change of the system, so they are quite very slow, so it's like a local equilibrium. So for the non-equilibrium, of course, you will have the heat transfer process, or actually, the transfer process is equal driving force divided by resistance. So driving force in here, it depends on the system what you want to calculate. For example, if you want to have the momentum, what's the driving force of the momentum? Velocity. Yeah, velocity is the driving force of the momentum. If you go for the heat, the driving force is the temperature. For the mass, the driving force is the concentrations, or you can see delta C, the concentration change. So these all the concept, if you take the red line, they are the same. Driving force divided by resistance. So resistance is what? What's kind of the resistance? Distance. So you can see that heat flux in here. We have heat because heat is consist between these two, conduction and convection. So for conduction, we can calculate based on the Qx equal to the minus Q delta T divided delta X. I think you learned this one in the unit operations. Yeah. So delta T, it's the driving force, and the resistance, it was delta X. So the other is concept is the same. Fourier's law, also the same. Yeah. So for the mass flux, we use the Fick's law. Fick's law is the same. Here is concentrations. So if you calculate the rho multiple by the the mass fractions, yeah. So in this case, you will have the concentration. This is the driving force of the concentration. And the same for the momentum. This is, we have the velocity. So driving force delta V. But if you say that delta X, delta Y, here it was the distance. So X, Y, Z for the Cartesians or rectangular. So you have R theta Z for the cylindrical systems. And for the spherical, you have the R theta C. So it depends on the kinds of unit that which kind of you want to use. Yeah, so I think this is thank you very much for the chapter 1 for the learning together for the thermodynamics principle. So then I will go for the mass transfers in the mass balance in the chapter 2. Thank you.